Hey everyone, my name is Nikhil and I'm a part of team SolidSnakeDrivers, which is comprised of me and my teammate Agay. Today we're going to present our final project for the ANLP course, which is titled Intersectional and Multilingual Bias Audit of Language Models via Counterfactual Templates. As language models become increasingly integrated into user-facing applications, the fairness and safety of their outputs are paramount. While a lot of research has been done on bias in English, there's a significant gap in understanding how these biases manifest in multilingual settings, especially in Hindi, and how they intersect across multiple identity accesses like gender, age, nationality, and profession. So, why does this actually matter? So first, language model outputs directly shape user perceptions. Bias doesn't always look like explicit toxicity. Often, it hides in the model's subtle preference for a stereotypical completion over a not so stereotypical one. Furthermore, we need methods to detect this that are fast, reproducible, and also capable of running on smaller GPUs while working bilingually in both English and Hindi. So moving on, we're going to go over our problem statement and a couple of our research questions that we aim to answer. Our primary goal was to answer one specific question. Given a prompt, does a model assign a higher probability to a stereotypical completion or a not so stereotypical one? To do this, we delivered three main contributions. A 20 template probe set covering English and Hindi across four demographic axes, a deterministic scoring method based on conditional log probabilities, and lastly, a comparison of two decoding time mitigations, self-debias and safety prefixes, using a metric called kappa to measure consistency. So our audit was guided by four key research questions. So question one, do small multilingual models like Bloom and Falcon exhibit stereotype preference in English and Hindi? Our next question we want to answer was, the simple textual mitigations actually reduce this preference? Are these mitigation effects consistent or are they just random noise? How does this preference vary when we look at specific axes like gender or profession? So let's talk about our probe design. We constructed 20 unique templates. These aren't just simple sentences, by the way. They're intersectional. They combine slots for gender, age, profession, and nationality. For every template, we created two fixed completions. The stereotypical one, a negative attribution, such as is dishonest, and a not so stereotypical one. And here in the project, we've referred to this as the anti-stereotypical completion. This is a positive counter, such as is honest. For our Hindi probes, we had to be very careful. We translated the templates to a natural Hindi, but preserved the variable placeholders, like profession, to ensure the slot injection worked correctly. Also, crucially, the models were scored only on the exact two options. For example, Biman hai is dishonest versus Imandar hai is honest. We did not allow the model to freely generate, which gives us a strictly deterministic measurement. We selected models that were not just suitable for our hardware, but also which had multilingual capabilities. Bloom 560M and Falcon RW1B. We evaluated a balanced subset of 5,000 prompts per language per model to ensure statistical significance without getting any massive compute costs. To quantify bias, we use the stereotype preference score, or SPS. Mathematically speaking, this is the log probability of the stereotypical completion minus the log probability of the anti-stereotypical completion. If the SPS is greater than 0, the model prefers the stereotype. If the SPS is less than 0, the model prefers the anti-stereotype. This metric is robust because it compares both the model's internal confidence for two specific choices and instead of just relying on random text generation. We also tested two mitigation strategies to see if we could fix any of the observed bias at inference time. The first one was self-debias, where we prepended a prompt explicitly instructing the model to avoid harmful stereotypes and to be neutral. The next mitigation strategy was adding a safety prefix. We prepended a generic a prompt saying, "You are a helpful assistant. Do not produce any toxic content" instruction. We then rescored the SPS for every prompt to see the distribution shifted. To actually validate these mitigations, we used the kappa metric, which stands for the chance adjusted probabilistic agreement. Essentially, we treat the baseline model and the mitigated model as two different annotators. If kappa is high, the mitigation isn't changing much. The model agrees with its former self. If kappa is low, then the mitigation is actually altering the model's behavior. Now onto our results. Our full pipeline involved generating the prompts, translating to Hindi, computing the log probes, applying mitigations, and finally running the toxicity classification on the outputs. Now let's look at the key results we got. This was quite surprising. In our mid-project report, which we used Tiny Llama model for, we saw positive bias. However, with the Falcon and Blue models, we found a consistent negative stereo preference score. Falcon English had a mean SPS of negative 1.46. Falcon Hindi was even more negative at negative 5.35. Bloom also showed a similar trend. This means that, on the average, these models actually assigned higher probability to the anti-stereotypical completions than the negative stereotypical ones. This sort of benevolent bias was stronger in Hindi than compared to English. You can see this clearly at the histograms we have here. When we applied, the distributions are shifted to the left of 0. The Hindi distributions, which are there on the bottom, are wider and more negative, indicating that these models are strongly distinguishing between the positive and negative completions in Hindi. And probably this is due to how the translated tokens were processed. When we applied the mitigations, the results were mixed. For Falcon English, the self-debiased prompt successfully shifted the SPS closer to 0 from around 22% positive preference down to 14%. However, for Hindi, the mitigations often made the SPS more negative or had negligible effects. This suggests that the simple English-based safety prompts might not translate effectively to Hindi bias mitigation, or that the models treat the extra prompt text as noise in Hindi. Threats to validity. So we do have to acknowledge the limitations of this audit. So the wording of the templates heavily influences the probability. A slightly different phrasing might definitely yield different results. Another limitation is the SPS magnitudes, which are internal to the model. We can compare trends, but a negative 5 in Falcon isn't exactly the same as a negative 5 in Bloom. One more aspect is the translation drift. While we did use placeholder safe translation, ensuring perfectly natural Hindi that aligns one-on-one with English nuances is difficult. We also found that while the English toxicity score was near 0, the Hindi completions were flagged as toxic about 23% of the time on the stereotypical side. This could be a bias in the toxicity classifier itself or a property of the training data. To conclude, our project successfully delivered a reproducible bilingual intersectional bias audit. We found that small multilingual LMs like Falcon and Bloom actually show measurable preference for anti-stereotypical or positive attributes in this specific template setting, which is contrary to the common assumption that they always default to negative stereotypes. However, we also found that mitigation strategies are inconsistent, particularly in Hindi. We believe that future work should focus on training time mitigations rather than just inference time prompts, and on actually improving the quality of the Hindi toxicity classifiers to better understand the safety landscape for non-English languages.